Hello everyone. I welcome you to this presentation on a propositional logic. So these are the objectives for this topic. So by the end of this unit, you should be able to explain the concept of propositions, apply operations on propositions by using truth tables. Just confirm if you are hearing me before I continue.
Clear.
Okay, so on this unit, you need to be able to explain the concept of propositions as well as applying operations on propositions by using truth tables. So, introduction, in developing a mathematical theory, assertions or statements are made. So these statements are made in the form of sentences using words and mathematical symbols. When proving a theory, let's say in mathematics, a mathematician uses a system of logic. So this is also the case when developing an algorithm for a program or system of programs in computer science. Sorry, I want to minimize something. So the system of logic is applied to decide if a statement follows from or is a logical consequences of one or more other statements. So logic is the start of the principles and methods that distinguishes between a valid and an invalid argument. So logic is the basis of all mathematical reasoning and of all automated reasoning. It is practical solution applications. It is practical applications, for example, to the design of computing machines, to the specifications of systems, artificial intelligence, to computer programming, to programming languages, and to other areas of computer science, as well as to many other fields of study. So this concept of logic is used in all these areas. They are still applied. So let's talk about a statement. Let's talk about a statement. A statement is an assertion or a declarative sentence that is either true or false, but not both. So for it to be a statement, it must be what? Either true or false, but not both. So it must have a truth value, and its truth value is either true or false, but it cannot be both. So a statement is also referred to as a proposition. So when you are talking about propositional logic, we are talking about statements, right? Because a proposition is also a what? A statement. So you can use these words interchangeably. So the truth value of a mathematical statement can be determined by application of known rules, axioms, and laws of mathematics. So use laws of mathematics to prove the truth or to determine the truth value of a what? Of a mathematical statement. So a statement which is true requires a proof. So if a statement is true, it requires a proof to prove that it is what? It is true. For example, we've got 2 plus 2 is equal to 4. It is Sunday today. This statement requires what? Requires a proof. If a proposition is true, its truth value is true. In a Boolean algebra, so you can use a 1 for true and 0 for false. But here we are just saying, let's use true for the truth value of our proposition if it is true. So if our proposition is true, so the truth value will be what? Will be true. So if a proposition is false, its truth value is what? is false. So the truth value is true and false are respectively denoted by the letters T and F, or by 1 or 0 respectively. So in our truth tables, you are going to see those T and F for true and for false. We are not going to use the 1 and 0s in this topic of propositional logic, not truth tables. I think we are going to use those 1 and 0s in a Boolean logic, in a Boolean algebra. So let's talk about a simple statement. We've got what we call a statement, and there is what we call a simple statement. So a simple or a primitive statement is a statement which cannot be broken down into anything simpler. In other words, it's a statement in its simplest form. So a simple statement is denoted by use of letters P, Q, and R, and there are many. You can even use W, you can use R, you can use S or any letter, but normally we use small letters P, Q, R or to denote what? A simple statement. Examples, we can have a statement P which says that there are 7 days in a week. So that one is a what? It's a simple statement on its own. And it is actually being represented by what? By a P. You can have this one. So here we are saying P is a simple statement. You can also have this one, which is say 3 plus 2 is equal to 6. It's also a statement whose truth value is what? Is false. And it's a what? And it's a simple statement. And it is represented by what? By R. So you can just write R such that, or R full colon. Can you make sure that all our mic are on mute? This is the problem of letting people in late in this meeting. They will be disturbing. I think in the future tutorials or the future presentations, we will not be allowing people to join later. Here, I'm sure there are almost about 6 people in the waiting list who want to join, and they'll be causing problems when you add them in. Okay, we are talking about a simple statement. So R is a simple statement. These are here. So these are more examples. So in propositions, we need to know which one is a proposition, which one is not a proposition, or which one is a statement and which one is not a statement, right? Let's talk about, if we say grass is green, you can determine if the grass is green and if it is not. So it has got a truth value of true or false. It cannot be both. The grass cannot be green and blue at the same time, or green and red at the same time. The grass is green. If it is green, is it green? Yes. If it is not, say what? It's a false. So this one is a simple statement. 4 plus 2 is equal to 6. It's a simple statement with a truth value false. This one 4 plus this one is truth value is true, and this one 4 plus 2 is equal to 7. It's also a simple statement with its truth value as what is false. So there are 4 fingers in a, here we are saying there are 4 fingers in a hand. This one is also a proposition, because you can actually say that this one, its truth value is what? It's false. Because we know that only a normal person have got what? 5 fingers in a hand. And these ones are all not propositions or are not statements. While if we say close the door, what will be its truth value? No, we cannot actually state it as something which is true or something which is false. x is greater than 2. We do not know the value of x, so we cannot say x is greater than 2. We do not have its truth value. Is it true or false? We do not know the value of x, unless if you are given the actual value here, not a variable. He is very rich. If we say he is very rich, who are we talking about? So that we can actually say that this guy also is very rich. Then from there, we can actually quantify if he is rich or not. Then we can actually determine its truth value or not. So these ones are not what propositions. I don't know if there are questions here. So if there are no questions, Tamengo, can you make sure that you switch off your camera and your mic and your microphone? Also, Mtetwa, can you make sure that you switch off your camera and your mic? Can we make sure that all our mic are on mute? Thank you. Can you make sure that all our mic are on mute? Can we make sure that all our mic are on mute? Understanding statements. X plus 2 is positive. This one is not a statement. Why? Because we do not know the value of what? Of x. So that we cannot determine that this one is positive or not. So it's not a statement because we do not have its truth value. Even here, if you say may I come in, is it a statement? There's no truth value there. Logic is interesting. It's a statement because we can actually say logic is interesting or not. If you say logic is interesting, is it interesting? So what is its truth value? If you say it is hot today, we can actually confirm if it is hot or not today. So there is a truth value for that, and it's a statement. If you say -1 is greater than 0, it's a statement because we can actually test to see if -1 is greater than 0 or not. So it have got a truth value of true or false, but in this one it's a truth value of what? Of false. For this one, x plus y is equal to 12 is not a statement. Why? Because x and y are variables. Those are not exact figures. So we do not know if x plus y is equal to 12 unless if we suggested the value of x and y. So it's not a statement. So let's talk about the compound statement. We've actually talked about a statement or about a proposition, and then we moved on to a simple statement or a simple proposition, and then now we are talking about a what? About a compound proposition or a compound statement. So a compound or a composite statement is a statement which is comprised of simple statements and logical operations or logical connectives. So instead of just being a single statement, it will be actually made up of more than one statement. So a compound statement is denoted by use of letters P, Q, and R, P, Q, R, and blah, 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 blah. But here you see that we have got what? Capital letters P, Q, and R. So examples of compound statements, there are 7 days in a week and 12 months in a year. So this end is forming what? Is forming a compound statement. This one on its one is a simple statement. This one is a simple statement, and we are using an AND operator. So this P is the compound statement, and this small p is the first simple statement that we are actually drawing from here. So there are 7 days in a week is a simple statement. There are 12 months in a year. It's also a simple statement which will be denoted by what? By Q. And then if we put all this together using the AND operator, we'll be forming what? we're performing this compound statement. So we also have this compound statement, here, which is being joined using an OR operation. So the grass is green or it is hot today. So the grass is green will be the first simple statement, and it is hot today is the second statement, and we are joining them using the OR operation. So we have this one, which also says that P is such that if it is not raining, then I will go outside and eat my lunch. So this one is a compound statement which uses if, then, and operations. So there is the if, then, and the and operation. So there are three statements which are being joined. There are three statements which are being joined. So it is raining is the first simple statement. From here, when you're saying if it is not raining, which means we require the negation of P. So the simple statement is that it is raining. Then I will go outside, which is also the second statement. I will eat my lunch is the what? Is the third statement. And then we are joining them using the if, then, and operations. I don't know if there are questions here. If there are no questions, then you can continue. This one is an exercise. You can do it on your own, which will be actually asking you to say if this one is a simple statement or not. If it is a simple statement, tell us the operation being used. You can attempt it. It is there in this slide, and the slide is on your photo. Like 2 plus 3 is equal to 5. Is it a simple statement? Yes. It is hot and sun outside. Is it a simple statement? No, it's a compound statement. Here it is hot and sun outside. And the operation is what is and. So you're just going to do that. So there are logical operations or logical connectives. Logical operations or logical connectives. Let's talk about this. There is the negation operation or the negation connectives. Its meaning it's not, and this is the symbol that you use. There is the conjunction, which is an and, and this is the symbol that we'll be using. There is the disjunction, which is the or, and you'll be using this symbol. There is the conditional, which is the if-then relationship, and use this symbol. And there is the biconditional, which is if and only if, and they use this symbol. So there are these examples that we have to do. Harare is the capital city, is the capital of Zimbabwe. Q is equal to 18 is divisible by what? By 3. Then if you say P and Q, you are using this. Sorry. You are using this and operator. You are saying P and Q, which means your statement in English should be Harare is the capital of Zimbabwe and 18 is divisible by 3. So you might be asked to transform this statement into symbol forms like this, or we can be asked to give the English version of this statement. So P or Q are saying Harare is the capital of Zimbabwe, or 18 is divisible by what? By 3. The negation, which is the not relation. So the negation of P, which is this one. So it will be like it is not the case that Harare is the capital of Zimbabwe, or simply just saying Harare is not the capital of Zimbabwe. Don't know if there are questions here. But Mansu, can you make sure that you are not sharing anything? I'm sure that everyone is actually seeing my slide. Also, can you make sure that you switch off your camera?
Say, may I please ask biconditional camera say up?
You will see it, but it will be actually using the if and only if, which means both the statements will be implying each other. You'll see it later. I'm sure that we are going to have an example on it. But the concept is just a simple. Can you make sure that you switch off your camera? If you are hearing me. Thank you. The idea is that both your statements will be implying each other. Like here, if we say P, if and only if, and if P and only if Q, we are just saying that P will be implying Q and the Q will be also imply P. So this one is necessary for this one is necessary for this one. Here we're being asked to translating from English to symbols. Like if you have got the English version and then you want the symbol or the symbols version, what do you do? So I've got this one which says let P be equal to it is hot and the Q be equal to it is sun, right? So the sentence that we have here, it is not hot. We want to translate it to its symbol form. So it is not hot, which is the negation of P. Because P says that it is hot. So the negation of P is it is not hot. So this will be your answer. It is hot and sun, which means we are going to use the AND operation to join the two statements P and Q. So it will be P and Q. It is hot and sun. Then we have what it is hot or sun, which means we are going to use the OR operation to join P and Q. So we'll be having P or Q. Also, we have got it is not hot but sun, which means we need the negation of this statement so that it will be saying it is not hot. So which means it is the negation of P. But is sun, which means we need an end. It is not hot, but is sun, just the same as saying it is not hot and it is what? It is sun. So we use the end operate. And then we've got this one, which is it is neither hot nor sun, which means it's the negation of this statement because it is not what? Hot. Which means it's the negation of P nor sun, which means it is also the negation of it is sun. And then we use the AND operation to join them. I don't know if there is any question here. There any question? Question Mongoli? You can ask. I'm sure I'm seeing a hand there. You can unmute yourself and ask your question. Question Munguli. You are on mute. You can unmute yourself and ask your question.
Any question on either or?
You've got a question or what?
A question,
Hello?
sir.
Yes.
Is there any question on either or?
A question on either or.
Yes.
If you are saying that it is either hot or it is sun.
Okay, so it will
Which
be
means it will be this statement. It is
all right.
hot or sun, because we are saying either hot or sun, so it will be P or Q. Or you can say it is sun or hot, which means it will be Q or P.
Okay, sir. Thank you.
Okay, you can also make sure that your camera is off.
Sorry.
Make sure that your camera is off. Your camera is on. Switch off your camera. There is a hand on audio Tanyarazo, audio. Is it a question or what?
Yeah, it's a question
Okay.
about whenever.
About
Whenever.
just form a statement on whenever. Was it all about English there?
Okay, like it is hot whenever it is sunny.
It is hot whenever it is sun, which
Yes.
means there is which means there is an implication there, which means that sun is implying it is hot. So P let me check. So the Q will be implying P, because we are saying it is hot whenever it, which means this one is the best condition. If it is sun, then it is hot. Don't know if you answered.
Yeah, I am. Thanks.
Okay, thank you. I think you can continue. There are no more hands. Okay, so examples for practice here. I've got this one. Let H, these are our simple statements that we are going to join to form the compound statements. So Tony is health, Tony is wealth, Tony is wise. These are our simple statements. So we want to translate the compound statements to symbolic form. So Tony is health and wealth, but not wise. We are saying Tony is what? Is health and wealth, which means Tony is health and wealth is H and W. You want to join them first, H and what? H and W, but not wise, which means we use an and, then we put that's the negation of what? Of S. So we put the negation of S here. Why? Because we are saying it's not what? Not wise. Tony is not wise. We can go on to this one, which says Tony is not wealth, which means it's the negation of W. Tony is not wealth. It's the negation of W. But he is health and wise. So you put an and you put this relationship is to health and what? And wise, which means H and S. Tony is neither health, wealth, nor wise, which means is the negation of all the three simple statements, and then use an and operator to join them, and then form this. Don't know if there are questions here. I think can also translate from symbols to English. It is something which is simple. but it's also very important to your module. So take it seriously. Let M be equal to Alex is good in mathematics. C be equal to Alex is a computer science student. Translate the following statement forms into what? The following statement forms into plain English. So we've got the negation of C. C says that Alex is a computer science student. So the negation, which is the not part, says Alex is not a computer science student. We've got something which says C or M, which means we're saying this is statement, this is statement, or this is statement. So Alex is a computer science student or good in maths. We've got this one which says M and negation of C, which means we are saying this is statement and the not part or the negation of this statement. So we are saying Alex is good in maths, but not a computer science student. So you can write it in many ways. Alex is good in maths, and Alex is not a what? A computer science student, because we are using an AND operator here. So a convenient method for analyzing a compound statement is to make a truth table for it. If you want to establish its truth values also, you need to use the concept of truth tables. So this will lend us on what? On the concept of truth tables. So a statement P can hold one of two truth values, which is true or what? Or false. Earlier we said that a statement must be either true or false. So a statement can hold one of the two truth values, which is true or what? Or false. So these are denoted by T and F respectively. T for true, F for false. Some books may use 1 for true and 0 for false. It's still the same again. So when determining the truth value for a compound statement, all possible combinations of the truth values of the statements comprising it must be considered. So if it is a compound statement, you need the truth values for the each and every simple statement, and then you join them as you go so that you can formulate the result. So this is done systematically by the use of truth tables. So therefore, a truth table specifies the truth value of a compound proposition for all possible truth values of its constituent propositions. So how do you construct a truth table? So to construct a truth table, assign each statement a column. So each and every statement that you have, it must have its own column. And then the number of rows in the table is determined by the number of statements. So for any statements, it will be 2 to the power n rows. 2 to the power n rows will be required. So for you to see the number of rows that you need on your truth table, you say 2 to the power n, where your n will be the number of statements in that compound statement. So systematically assign assign truth values to each of the statements, beginning in the first column. After assigning your truth value, once all possible truth values for the simple statements are inserted, determine the truth values of the compound statement following the rules for the operations. So you'll be following the rules of what? Of operations. If it is an AND, what will be the result of true and true? Something like that. So let's talk about the truth let's talk about the truth table for the negation. From here, we say that the rules for the operations, we are going to use the rules for the operations. So we know that here we've got these operations. We've got the not, we've got the add, we've got the or, we've got the if then, and if and only if. So all these operations have got their rules that we have to use. So we are going to do those rules. So we are going to start with the negation. Let me add these two people. So here, if P is a statement, the negation of P is not P, or it is not the case that P, and it is denoted by the negation of P, right? So we said that when you are creating a truth table, you need to know the number of rows, right? And then you need to actually give each and every statement its column. So here we've got the statement that we have is only P. So it will be 2 to the power n, which is 2 to the power 1. So that's why we have got 2 rows here. And then we need the column for P, which is our statement. And also we need the column for the result, which is the negation of P, right? So here you use the half and half rule to assign the truth values. Like here you've got true and false. If there were 4 rows, you are going to say true, true, then false, false, something like that. So here we are going to start by true, then you put false. You can actually also start by the false values and then followed by the truth values. By true values, there's no problem with that. But let's just use this one. So you put a true here and a false here. These are the truth values for P. Because it's just a single statement, it have got 2 values, true and what? And false, right? Then from there, we'll be actually doing the negation operation. So let's say the negation of true is what? Is false. The negation of false is what? Is true. So this will be the truth table for the negation operation. So whenever you are going to find the negation of true, you are going to get false. When you are going to find the negation of false, you are going to get a what? A true, because it's like you'll be flipping. Just as simple as that. This will be your what? Your truth tables. So this operation is as it stands, it's very simple because it's like it is standing alone. When it gets mixed with others, you are going to see that it will be actually maybe complex also. So just master it as it is here, and then you apply it later. Can you make sure that, let me help you, Ben. Fine. Conjunction, let's use the conjunction, the AND operator. The AND operator. So if P and Q are statements, then the conjunction of P and Q is P and Q. And it is denoted as what? P and Q using this symbol. So it is true when and only when both P and Q are true. Whenever we have got this P and Q, their truth values are true, then that's when this P and Q is going to be what? To be true. So if either P or Q is false, or if both are false, P and Q is what? Is false. So this is the truth table for P and Q. So team, you need to master this, so that whenever you are given 2 statements and then they are using the AND operator, and then you are asked to actually give a truth table, you'll be actually knowing that whenever I've got a true and a false, which one is going to be my truth value for the P and Q. So let's go again on creating this truth table. Here I've got 2 statements. We've got P and Q, right? So it will be 2 to the power 2, which will be 4. So which means we need 4 rows. Which means this one, 1, 2, 3, 4. And then we need 4 rows, and then the half of 4 is 2. So we are going to write true, true, and then false, false. And then for the next column, first we've actually put P here, Then for the next column, we write true, false, true, false. Why true, false, true, false? Because the half of this one will be 1. So it will be actually true, false, and then here also true, false. Something like that. And then we need the column for our result. When you say P and Q, what will be our result? So we need this column for our result. So when you say true and true, what will be our value is what? It will be true. If we say true and false, it will be false. False and true, it will be false. False and false, it will be false. So it is only true whenever our inputs are all true, or the value, the truth value for P and Q are both true. I don't know if there is any question here. If there are no questions, I think we can move on to the disjunction, which is the oral part. So if P and Q are statements, then the disjunction of P and Q is P or Q. And it is denoted by P or Q. This is simple. So it is true when at least one of P or Q is true. Sorry, I need to take this call. Sorry, I'm back. So, question, Mnguli, is it a hint? You can ask if it is a question then. Question, Mnguli. I'm seeing a hand on you.
Yes, sir. Hello.
If it is a question, just ask.
Yes, sir. I want to ask you whether I'm wrong or I'm correct. I want to relate this true or false. There is same as these operations plus, minus, minus.
Like what?
Like the operations plus, minus.
I don't know where are you coming from, like, but
Just
here
relating on the operations.
These operations, if it is an OR, it's an OR gate, something like an OR gate in a logical,
Okay.
or in a Boolean algebra, so something like that. It's an OR gate. When you say P or Q, and then the T and F, those are truth values. For P, it is either true or false because it's a statement.
All right.
Yeah,
so whenever there is a false and a true, the answer will be always false.
If it was what?
True. Whenever the row is what in the result will be false.
Sorry, there is a background noise there.
All right. Say I'm asking on the result. For example, if the answer is the statement has got a true and false, the result.
If it is true and false, If you are using the
Yes.
AND operator, are you referring to
Always be false.
are you referring to this one AND operator to this AND operator?
Yes.
Yeah. Yes, if it is an AND, it is only true whenever all your inputs are true.
Okay.
If P is true and Q is true, then it will be true. But otherwise, it is what? It is false.
Okay.
Yes,
I
whenever one
thank you, sir.
input is false, then output is false. It's okay, thank you.
Uh-huh. All right.
Then for the disjunction, here, the P is what? P or Q? Just want to show that one. Okay. So true or true is what? Is true. True or false is true. False or true is true. And then false or false is what? Is false. For this one, for the disjunction or the OR operation, for it to be easy for you, just take it as we have got two conditions. When we say that if one of them is true, then we can do this. For example, if the first statement is true and the second statement is true, or the second statement is true, we can do something. So it is true. If the first statement is true, then or it is false, we can still do that because we've got the truth value true at one of the what of the input. The same as here, P is false, but Q is what is true. So we can still do something. But here it is false and here it is false. So we can do nothing. So it is only false when both the inputs have got the truth value F or the truth value false. Then there is the exclusive disjunction. Exclusive disjunction. So the exclusive disjunction of P and Q is symbolized by P and this plus in a circle and then Q. So this compound proposition is true when exactly one of its components is true. The truth table of P exclusive disjunction Q is as this. So for this one, take an example of an issue of less than or equal to, where we say that this must be less than or equal to so that we can do something. So if we say that it is either true, here we've got it true and what and true here, it will give us what? A false. If it is also a true here and a false here, it will give you true. If it is a false and true here, it will give you a true. But if it is false and false here, it will give you a false. So it is only true when one of the inputs is what? Is true. Otherwise, it is false. Like if you say that if one is less than or equal to 2, you are going to do something and our P will be our 1 and our Q is something like that. So is it this one less than or equal to this one? Something like that. That's where the exclusive disjunction came in. So when two simple propositions are combined using OR, Context will provide the clue as to whether the inclusive or exclusive sense is intended. So there is the less than or equal to, or the less than, or the greater than or equal to, or the greater than, something like that. So tomorrow I will go swimming or play football. Seems to suggest that I will not do both and therefore becomes exclusive, or like you cannot do both. You cannot go swimming at the same time playing football. So it's either you go for swimming or you play football. So if this event is true, this one will be false. If this one is true, if this one is false, this one will be true, something like that. So it will be what? The exclusive or a part. There is no inclusive. So applicants for this post must be over 25, or have at least 3 years relevant experience. Suggests that applicants who satisfy both criteria will be considered. Therefore, or becomes the inclusive form. So where context does not resolve the ambiguity surrounding the word or, the intended sense can be made clear by affixing or both to indicate an inclusive reading. So in other words, if there is no such context, you need to use this disjunction or part, this one. Otherwise, the context will be provided. So where there is no clue as to which interpretation is stated and the context does not make this clear, then oral is conventionally taken in its inclusive sense. So let's talk about the conditional if then, which is the implies statements. So also known as the implication. Also known as the implication. So consider the statement: if you earn an A in a math, then I will buy you a computer. So this statement is made up of two similar statements. You earn an A in maths, and also I will buy you a computer. There's this P and Q statement. So the original statement is then saying if P is true, then Q is true, or more simply, if P, then Q. So we are saying if this one is true, if you pass, or if you earn an A in a maths, then I will buy you a computer. So we can also phrase this as P implies Q, and we write P implies Q, something like this. So conditional statements, if P and Q are statement variables, if P and Q are statement variables, the conditional of Q by P is P then Q, or P implies Q, and is denoted by what? By P implies Q. It is only false when P is true and Q is false. So whenever true implies false, it will be false. Otherwise, it's what? It's true on the truth table. So the arrow, this one, is the conditional operator. And in P implies Q, the statement P is called the hypothesis, and Q is called the conclusion. So here is the truth table for P implies Q. So true implies true, which is also true, but true implies false. Hakuna chokwadi chinoti nema. So true implies false. It's what? It's false. Then false implies true. It's what? It's true. Kana ema idziti nema kana dzakutibuditsira chokwadi ichi ichokwadi. So false implies false. It's also true. And it is nema dzinotipe nema. So false is what? False implies false is also true. So that's the implication there. It is only false when it true implies false. So it can come in combined with other operators. You just need to know this one for what? For this part of the implication. Then other ways of expressing implications. I don't know if there are questions here. Innocent Chide, raise it a hand.
Yes, sir.
Yeah, you can ask.
Sorry, can you take my solution? Maybe the but it's 2 to the power n by yeah. But that is 2 to the power n, but that's 2 to the power 4. But that's 2 to the power 2, but that's one answer 4. My rows and columns, the dominant of one is 0.
All right. It's fine. We don't have to beat a wrap up. What we are saying here is that if you want to create a truth tables, there are simple rules that you need to follow. Like here, we have got a number of what? Of rows that we need. And the formula for that is 2 to the power n, where n is the number of statements that will be involved in that compound statement. Like here, our compound statement, there is a background noise on your mic. Okay, it's fine. So for 2 to the power n here, where your n is what is the number of statements that of simple statements in your compound statement. So here I've got 2 statements, which is a p and a q. So it will be 2 to the power 2 to the power 2, and then we get 4 rows, which means it's a 1, 2, 3, and 4 rows. So your truth table will be having 4 rows, besides this one for headings. Then from there, you need to assign each and every statement its column. So you are going to create a column for statement P and for statement Q and for the result, which is P implies Q. And after that, you need to put the truth values starting from the first column, the truth values of the what? Of the statements here. So since we have got 4 rows here, you use the half rule. So firstly, you put true, true, and then you put false, false. Because we have got 4 rows. So the first 2 rows you put true, and then the second, the last 2 rows you put false, false. If they were 8, you're going to put 4. Here it was going to be true, 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 true. Then you put false, 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 false. And then for the second one, you do a half of the what? Of the first rows. Like here, we have put true, true. So you put only 1 true and then followed by a false, and then only 1 true and then followed by a false. And then these ones, you'll be actually formulating them after using this operator. You'll be saying true, P implies Q, which will be true implies true, which is true. True implies false, which will be false. False implies true, which will be true. False implies false, which will be also true. I don't know if you are well answered on the creating.
Yeah.
Right. It's okay, thank you. Then EMRI, there is a hand there. What's the issue?
I think I was asked.
It's okay, thank you. So let's talk about other ways of expressing implications. So the implication P implies Q could be expressed in many alternative ways, such as if P, then Q, or we can just say P implies Q. We can just say not P unless Q, say Q follows from P, or Q if P, or if P, Q, P only if Q, or Q whenever P, or P is sufficient for Q, or Q is necessary for P. I'm sure this one was the question was this question was raised earlier on whenever issue. When you say Q whenever P, it's an implication. We are saying that this P implies Q because Q whenever P, or whenever P, which means we need P for Q to occur. More about conditional statements. So given the conditional proposition, P implies Q, we define the following. The converse, there is the converse, the inverse, and the contrapositive of the conditional statement. You need to know that. So the converse of P implies Q, it will be Q implies P. Instead of P implying Q, it will be actually Q implies P. And then the inverse, if you are being asked to find the inverse of a conditional statement, P implies Q, it will be the negation of P implies the negation of Q. So you simply negate both the statements there, P and Q. Then the contrapositive of P implies Q, it will be now the negation of Q implies the negation of P. Don't know if there is any question here. Just a matter of knowing. If you need the contrapositive, you just take the inverse and then you interchange the statements there. Instead of the negation of P being implied the negation of Q, it will be the negation of Q implying the negation of P. Something like that, or you can just take the converse there and put the negation precise. That would be a contrapositive. So the truth table gives conditional values for its converse, inverse, and contrapositive. Like here, we've got these two statements, P and Q. If you see on our column, we only have P and Q. So we've got two statements, which means we've got 4 rows, this one, this one, this one, this one. So you put true, true, false, false, true, false, true, false, true, false. And then P implies Q. We know the truth table of the truth values for P implies Q. It is only false when true implies false. So whenever T implies false, it will be false. Otherwise, it is true. So this is the truth values for P implies Q. Then for Q implies P. Then now we are saying true implies true, then it is true. False implies true, it is true. But when true implies false, it is what? It is false. And then when false implies false, it is what? It is true. And then for the negation of P implies the negation of Q. I think here you need a separate table, a separate column for the negation of P and for the negation of Q to use. Why? Because you cannot actually do it directly here. We are saying the negation of P implies the negation of Q, which means the negation of P is false here, and the negation of Q is what is false here. So it will be false implies false. That's why we've got a true here. And then here it will be this one, we flip it because it's the negation of P, it will become false. And this one, we flip it, it will become true. And then we say false implies true, then it will be true. Then here to be true implies false, which is false. Then it will be true implies true, which will be true. The same as here, it will be easier if we put the negation, the column for the negation of Q and the column for the negation of P, so that we'll be dealing with those two columns rather than starting by flipping these ones. So you are saying this column implies this column, but with the negation, and here with the negation. So the negation of this, it will be false, and this one, it will be false. So false implies false, yes, it will be true. Then true implies false, it will be false. Then false implies true, it will be true, and then true implies true, it will be what? It will be true. So that's about the converse, the inverse, and the contrapositive. Here, the converse of P implies Q, it will be Q implies P, which is here. This one will be your converse. And then if we come here, the inverse of P implies Q, it will be the negation of P implies the negation of Q, which will be this one. And then the last one will be the contrapositive, where the negation of Q implies the negation of P, this one. So these are the values for the contrapositive. I don't know if there are questions here. Okay, I think we can erase against our time now. So this one is an exercise. State the converse, the inverse, and the contrapositive of the proposition. We've got if you check, place is
sorry, sir, to disturb. There is a hand from Gon.
There is a hand from Gon. Okay, you can ask Gon.
Okay, say, I wanted to ask Kuti if there are a question where in for my inputs. Tinocha boss atikana tine two my inputs tinoisa two table in a function. Then you can in 3 with put 8. Kokane 4.
It's 2 to the power 4. 2 to the power 4 is what?
Okay.
Is it 16? Then you need 16 rows. And then the first one, the first column will be having the first 8 columns will be having your true, or you can put false, 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 false. Then later you can put true, true, true to the last 8. And then the next column you'll be putting the first 4 as false, false, false. If you're actually using the first column, also if you put the first false. But let's stick to the idea that we're using of using the first one, true values. So on the first column, the first 8, it will be true, 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 and then false, 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 false. Then on the second column, it will be the first 4, it will be true, and then the next one, the next 4, it will be false, and then the next one true. So, and it goes just like that. The next one, the first 2, true, true, and then the other one, false, false, true, true, false, false, true, true, false, false, and the last one it will be true, false, true, false, true, false, up to 16. I don't know, Ngoni, is it still a hand?
No, sir.
It's okay, thank you. If you understand, or if you get it. So here we've got this example. If Jack plays his guitar, then Sarah will sing. So if Jack plays his guitar, then Sarah will sing. You are being asked to give or to state, just state the converse and the inverse and the contrapositive of this statement. Also, you'll be actually asked to state the converse, the inverse, and the contrapositive of the proposition. If it's not Sunday, then the supermarket is open until midnight. Sorry here. Okay. So, possible solution on the first proposition, we define P as Jack plays his guitar, and then Q as Sarah will sing. So the first thing is to simplify or to write that compound statement in its simple statements. Can we make sure that all our mic are on mute? So that P implies Q. Opening. George, so you are unmuting yourself. I don't know what's happening there. Or if it is just another way of asking me to remove him. So, I think it's not fair. You are disturbing us. So P implies Q. If Jack plays his guitar, then Sarah will sing. This is the P implies Q that we're actually having here. Which is if Jack plays his guitar, then Sarah will sing. Then the converse of P implies Q. It is Q implies P. You just need to interchange these two for the converse. So it will be, if Sarah will sing, then Jack plays his guitar. Then the inverse, it will be the negation of P implies the negation of Q. So we are just putting the negation on the converse statement. So if Jack doesn't play his guitar, then Sarah won't sing. Then the contrapositive, the negation of Q implies the negation of P. Contrapositive, if Q implies the negation of P, then if Sarah won't sing, then Jack doesn't play his guitar. So this is the converse, the inverse, and the contrapositive of this proposition, of this compound proposition, if then. Then the inverse of conditional statements. Let's talk about the truth table of the inverse of the conditional statement. So the inverse of the conditional statement, P implies Q, is the negation of P implies the negation of Q. And a conditional and its inverse are not equivalent. You need to know that the conditional statement and its inverse are not equivalent, as could be seen from the truth table. So we've got these two statements, P and Q, and we've got their truth values, true, true, false, false, true, false, true, false. And then we've got the P implies Q, which is our first statement. This one, we look at this column as well at this one, which is our inverse. This one is our inverse, this statement. So we need to see if this one is equivalent to this one. So here I've got a true and here I've got true, which is yes, but here I've got false and here I've got a true, which means this one is not equal to this one, and here I've got a true and here I've got a false, here I've got a true, here I've got a true. So if they were equivalent, all these values were going to match with each other in each and every row. Like here, true, true. Here maybe it was going to be also true, and here true. Then here true, maybe here true also, so that it will be equivalent. So the conditional statement and its inverse, they are not equal. And you see the way that this truth table is actually constructed. We add these additional columns, the negation of P and the negation of Q. Why? Because we wanted to use them. So this is the best thing that you can also do whenever you are being asked to give the truth values of this statement from this statement. Because you are going to use this one, like here, you need to find the negation of P and the negation of Q, so that whenever you are saying the negation of P plus the negation of Q, you'll be saying false implies false, and then you give a value here, rather than to first flip this one so that it will be false and false, then say false implies false, something like that. Then let's talk about the biconditional, if and only if. There is the if and only if. So if P and Q are statement variables, the biconditional of P and Q is P if and only if Q, and is denoted by P with this double arrow, then Q. If and only if is abbreviated as IFF, which is if and only if. So the double-headed arrow is the biconditional operator. And then this is truth table. So true if and only if true is what is true, then true implies false and false. This one will be false. Why? Because we are saying true implies false, and we are saying at the same time we are saying false implies true. So for false implies true is fine, but for true implies false is what? It's false. So overall we put a what? We put a false here. False implies true and true implies false here. We put what? A false. And then false implies false, false implies false. It's always what? True. So you put a what? A true here. So it is only true whenever it have got the same input. Whenever you have a true and a false, that's when it is true for the if and only if part. So the biconditional if and only if alternative wording for that can be P if and only if Q, or P if Q, or P implies and is implied by Q, or P is equivalent to Q, or P is a necessary and sufficient condition for Q. I don't know if there are questions here. So if there are no questions, order of operation for logical operators. There is an order of operation, just like what we are doing in body mass on applying addition, subtraction, division, also something like that. So also here in the propositional logic, also have the order of operation. So the order of operation for logical operators is as follows. Evaluate negations first. So whenever there is a negation, evaluate the negation first. Then evaluate the or and the end second. So this true will follow. When both are present, parentheses may be needed. Otherwise, work left to right. So whenever they are there, they are both there, the end, the or and the end. Parentheses will guide you. You start with the ones which are in parentheses. If there are no parentheses, just work from left to right. Then evaluate, after that, evaluate the implication and the if and only if. This one. So when both are present, parentheses may be needed. Otherwise, work from left to right. Use of parentheses will determine order of operations, which override the above order. So if there are parentheses, start with the what? With the parentheses. So the summary that we can draw here, or what we have done, what is a statement, how a compound statement is formed, logical connectives or the negation, the conjunction, the disjunction, how to construct a truth table for a statement form. This is what we have actually covered. So there is what we call a tautology. I don't know if there are questions before we continue here. Because by 3, I'm sure we need to be through the presentation is that short. So a tautology is a statement form that is always true regardless of the truth values of the statement variables. So you are saying if a statement is tautology or is a tautology, all its values will be true regardless of what of the input values. For example, the statement form P or the negation of P is a tautology. Why? Because here we've got our input of P and the negation of P. And if you see here, we all have what? True in this result column. So it is a tautology. So if there is something here which is true, then it is not what? A tautology. Then there's what we call a contradiction. A contradiction is a statement form that is always false, regardless of the truth values of the statement variables. Yeah. So the output will be always false. So a contradiction is represented by the symbol sin. So if we have to prove that a given statement form is contradiction, we will make the truth table for the statement form. And if in the column of the given statement form, all the entries are F, then we say that the statement form is contradiction. For example, the statement form P and the negation of P is a contradiction. As it is shown here, since in the last column in the truth table we have got F in all the entries, so is a contradiction. P and the negation of P is identical to what? Contradiction. C. Like you've got our input P and the negation of P, and you see that on our output here, of course, the false only. So it is a contradiction. Here are some remarks. Most statements are neither tautologies nor contradictions. I say most statements, not all. So a proposition that is neither tautology nor a contradiction is called a contingent. So something which is not a tautology and something which is not a contradiction is a what? A contingent. So the negation of a tautology, is a contradiction, and vice versa is also true. So the negation of a tautology will give us a contradiction. The negation of a contradiction will give us a tautology. Since here, if we negate this one, the negation of this one will give us true, which will be a tautology. So in common usage, we sometimes say that two statements are contradictory. By this, we mean that their conjunction is a contradiction. They cannot both be true. So let's talk about the logical equivalence. Logical equivalence. So two compound propositions are called logically equivalent if and only if they have the same truth values, no matter what truth value their constituent proposition they have. So no matter the inputs, they must have the what? They must have same truth values. For instance, P implies Q and the negation of P or Q are logically equivalent. And you can write it as P implies Q is identical. We do not use the equal sign, it's identical to negation of P or Q. Note that if two propositions P and Q are logically equivalent, then P implies Q and Q implies P is a tautology. This one, if and only if, simple. So to determine if two statements P and Q are logically equivalent, construct a full truth table for each statement. So you need to construct a full truth table for this one and for this one. So they might be on the same truth table, but they will be actually having you must have a column for this and a column for this. So if their truth values are at the main connectives are identical, the statements are equivalent. Alternatively, show P implies Q and Q implies P is a tautology, and hence conclude that P is identical to Q. So here, show that P implies Q is identical to the negation of P or the negation of Q. So what we do, we check on this column and this column. If they are identical or they are equivalent, each and every row must have the same value. So we can actually say these two statements are what? Are equivalent. So here's the practice. Using truth tables show that following propositions are logically equivalent. So for the issue of equivalence, you can use the truth tables, or you can use the equivalent laws, or the laws of what? Of logic. So if the question is silent about that, you can choose what you want to use. But if the question is not silent, use what you are being asked to apply. This one also goes to the set theory. If you are being asked in your assignment 1, there was a question which was asking you to use set identities. There are set identities laws. They are there on your portal. Use those laws if your question is not silent about that. If it is not referring to use the set identities, you can use other methods like those of direct proof that others were trying to use. It's also still fine. But let's check on that. So here we can do a truth table with this and these two columns, and then you check if they are equivalent. You can also do another truth table with this and this, and also you can do another truth table to prove the De Morgan's laws with this and these two columns, and then you check if they are equivalent. You can do the same with these ones. But I do not have the truth tables for that. So you need to do those. So there is what we call the laws of logic. I don't know how are you going to know them, but you need to know them. I don't know if cramming is going to help you. I don't know. But if you keep on practicing them, I think it will also help you. So there is the commutative law. There is implication laws. There is the exportation law, the equivalence, the reduction ad absurdum, and the De Morgan's laws. So you need, for you, what you need to know is just how to apply them. So if you are given something like this, you can actually interchangeably using this one. If you have something like this P and Q, you can also use the Q or a P. If there is P and Q, you can also use the Q and P. It's just what? The same by the commutative law. On the implication laws, if P implies Q, it's just the same as negation of P implies Q. It is also identical to the negation of the parenthesis here of P and negation of Q. So this is what all this mean. On De Morgan's law, do the same. This one, you can substitute this one with this, right? Though I do not advise you to do a lot on them. So associative laws, but please, they are very important. Just read them, go through them, you see them when you'll be doing discrete mathematics, and you'll be like, our lecturer did actually taught us on these laws or so, rather, because you'll be actually not being, we will not teach you again on these laws. So there is the associative laws, the distributive laws, double negation, the identity laws, negation or the complement laws, the idempotent laws, absorption laws. You need to go through them. So here is the application of the laws of logic. Here I'm going to show you how are you going to apply them. So if you are being asked to rewrite the statement forms without using the symbols, it implies this one, the if, then, and then the if and only if, this part. So P and negation of Q implies R. You are being asked to rewrite this one without this symbol here. So what are you going to do? This one says P and negation of P implies R. And then we know that we have actually done the order of operations, right? When we say that the negation first, then followed by the and then the implies you follow later. So this is, we are putting parentheses to show that this is the first thing that we need to solve. So it's what is the order of operations. So it is good also to mention the law that you have used. Then from there, we can use the implication law to remove this implication. How? You can just put a negation on a P, and then you put an or here, and then you put your Q. I think this is the law. If you go on to the implication law here, if you go to P implies Q, you can put negation P or Q. So the left hand, or everything on the left hand will be our P, and everything on the right hand, which is our R, will be our something like that. So this is what we are going to have, the negation of this P or our Q. So this will be our P and this will be our Q. So you just negate P and then you put an or, and then you put your Q. So it will be the negation of this P and the negation of Q, and then you put an R. So this is our, we use the implication law. So we managed to remove this. So it's enough for this question. Any further simplification or so, it's not necessary, because you have actually been, you were asked to remove this implication. Then for this one, for this question, can do the same. When you came here, I've got P implies R and Q implies R. It will be identical to, then you need to use the implication law. The implication law where on these two, because we have got parentheses. So the order of operation, we first work on parentheses. So we need to remove this implication. So whenever we have got P implies R, we can use the negation of P or Q. So which means it will be the negation of P or R, and here it will be the negation of Q or R. And then from there, we want to remove this sign. So we're going to use the equivalence of biconditional. So the equivalence of biconditional is that this one will imply this one, or and this one will also imply this one. So this is what we have, this one implying this one, and this one imply this one. So this is the biconditional, the equivalence of biconditional. Whichever side you go with, you are going to just get the same result. So you use an and, then after that, we use the implication law again to remove this implication. So it will be this one implies this one, it will be the negation of this or the or this one. So it will give us negation of the negation of P or R. Then you put an or here, and then you put this one as it is, and then you do the same this side. So practice, rewrite the statement form negation of P or R or Q implies R, or negation of Q to a logical equivalent form that use only negation and an N. here. So this one is a practice for you that you can go through. And this one is the solution. You are given this statement and you are being asked to remove this thing and use only an and a negation. So we need to remove this or and this or and this implication. So on order of operation, first we need to solve or to resolve those with a negation. So this is why you've put the parentheses here and here. And then from there, we use the implication law, which says P implies Q is the same as the negation of P and the negation of Q, because we want to remove the or. So we do not want to use the other one with the or. So on the implication or removing this one, you say negation of P or Q. So the negation of or of P or Q, then you put an and, then the negation of what? Of our Q, which is this one. After that, you use the De Morgan's law to remove this or part. If you go to the De Morgan's laws, here, this one is the distributive. So the De Morgan's law says the negation of P or Q is the same as the negation of P and Q. So whenever you have an or and you want to remove and replace it with an and, you use the De Morgan's laws. So this is the law that we have applied. Come to this. So this will be an exercise for you to do. You can actually exercise on it. I don't know if there are questions, because this is the end of our presentation. Are there any questions?
No, sir.
Okay. Others, do you have any questions or contributions? They are also welcome.
Thank you, sir.
Okay. Kumbula, I'm seeing a hand on you, Kumbula. Kumbula Osman or so, something like that. Is it a contribution or a question? You can ask. You can contribute. You can unmute yourself, Kumbula.
I don't know if no one read that lecture for revision or for to play it later.
Yes, I'll upload it and
All
share
right.
with you the link.
Okay, thank you. Okay.
So if there are no more questions or contribution, you can call it a day. So have a good day, team.